Hi, this is Ross Anderson. I am your TA for Fundamentals of Probability, and this is the rehearsal for Recitation 1. So today we're doing a review of real analysis. So I guess we will start at the very beginning. The basic building block in real analysis is sets. So set is an unordered collection of unique elements. So the keywords here are unordered and unique. So let's just do a few examples. We saw this one in class already, but the outcomes for coin toss. Coin toss outcomes. So it could be heads or tails. So you can see that the elements of the set, they don't really have to be numerical values. They can just be anything as long as they're unique. Another example, the days of the week. So here we have Monday, Tuesday, up to Sunday. The real numbers. So these are going to be denoted by R in this class. We can make more complicated sets. So we could say something like X, Y in R2, such that X squared plus Y squared less than or equal to 1. So if you aren't familiar with this R squared notation, we're going to talk about it later in class, but you should recognize this formula. It's just a circle with radius 1. So this is the set of points inside the circle. And you can also do things like the closed interval 1, 2, and this is just the points x such that 1 less than or equal to x less than or equal to 2, or an open interval 1, 2, and here it's kind of similar, except now we have strict inequality. Okay, so there are lots of examples of sets, and you've probably seen most of these before, but we're going to talk in much greater depth about them. So first let's talk about the basic set operations. Okay, so these should be hopefully familiar to you. You should have seen them in undergrad, and also you saw them in class. So we have the union. So if we have two sets A and B, A union B, written like this, these are just the points x such that x is in A or x is in B. We have intersection, and so we write this A intersect B, and these are the points x such that x is in A and x is in B. We have the complement. So this requires some kind of reference set. So we'll just call the reference set omega here. So we'd say A complement is x in big omega such that x is not in A. And finally we have a set difference. And you can write this as A set difference B. What is this? These are the points x in A such that x is not in B. So as an exercise to yourself, you should see that it is possible to write set difference in terms of these other operations. Okay, so now let's do a few examples using these operations. So these are just really basic examples, but don't worry, things will get more difficult soon. So again, we're going to stick with the days of the week. Okay, so we're going to let the set A be the days with lecture for this class. Days with probability lecture. So this semester, that would be Monday and Wednesday. Let B be the set of days with recitation. So that's just Friday. Let C be the weekdays. So this is Monday, Tuesday, Wednesday, Thursday, Friday. Okay, so let's just do a few very quick examples. So what is A union B? Well, of course, it is Monday, Wednesday, and Friday, because we want all the elements from A and we want all the elements from B. What is A union C? So we see that A had Monday, Wednesday, C had Monday through Friday, which includes everything in Monday, Wednesday. So this is actually just the same thing as C. We're not adding any new elements. So just to write it out, Monday, Tuesday, Wednesday, Thursday, Friday. Okay. What is A intersect B? So we want everything that's in both A and B. There's nothing there. That's just the empty set. And in this class, we are going to write the empty set like this. This is standard. This is the empty set. And finally, let's just say, what is C complement? So what complement are we taking this with respect to? Well, it's the days of the week, Monday through Friday. So that we want everything that is not in Monday, or it's Monday through Sunday is the days of the week. That's the overall set. And we need to take things that are not in Monday through Friday, but are a day of the week. So this is just Saturday and Sunday. Okay, so that was pretty simple. We should do a set difference example too. So let's just take C set difference A. So it's Monday through Friday without Monday and Wednesday. So this is just Tuesday, Thursday, Friday. And if we did A without C, what do we get? So A has Monday, Wednesday. We take out everything in C, there's nothing left. So we just get, again, the empty set. Okay. So that was a pretty simple example. Don't worry, things will get more difficult soon. So let's talk about comparison of sets. Okay, so we have the most basic relation is the subset relation. So we will say that A is a subset of B. A is if every element in A is also in B. Okay, so less commonly used is the so-called subset, at least in LaTeX, and that's written A subset B, and this is the same thing as B is a subset of A. It's more standard to use this form than this form, but if you write this, I'll know what you mean. And finally, we have equality. And what is equality for sets? So we write it A is equal to B. What does it mean? It means that A is a subset of B and B is a subset of A. Or alternatively, you could just say that every element in A is in B and every element in B is in A, or A and B have the same elements. A have the same elements. Okay, so let's just do a few more examples. Make sure this is clear, because if it's not clear, you're going to be in a lot of trouble later. Okay, so the open interval, 1, 2, this is a subset of the closed interval, 1, 2. Why? So the only difference between these two sets is that the endpoints are excluded from the open interval. Okay, another really simple example. Monday, Wednesday is a subset of Monday, Wednesday, Friday. And finally, Monday, Wednesday. This is equal to Wednesday, Monday. Why is this the case? Because the order does not matter for sets. The order is completely irrelevant. Okay, so let's move on. Okay, so this is a topic that may be a little bit less familiar to you guys, but if you took real analysis, you should know it. So we are on page 4 now, I believe. Let's talk about logical quantifiers. This is a very important topic. This is kind of the language of mathematics. All proofs should be stated in the language of logical quantifiers. Okay, so what are they? They're used, well, what are they for? They're used to make statements about sets and their elements. Okay, so there are two types. I think hopefully after I tell you what they are, you'll realize that you already know what these are intuitively, at least. So the first is for all, or sometimes it's called for every or for each. And the symbol used to denote this is this kind of upside down triangle. And this is like an and. So let me just give you an example of how it's used. So you could say, let's say that we have x is some subset of the integers. Here, this z denotes the integers. Y is a subset of the integers. Sorry, y is just an integer. Y is an integer. So here's a statement that uses a logical quantifier. I could say that for every integer x in the set x, y is greater than x. So y was an integer, remember, and x is integers, so we can compare them. And so this is saying that if we were to just enumerate the elements of x, so let's say that big X is just x1, x2, xn. What this is saying is that y is greater than x1 and y is greater than x2 and y is greater than xn. Okay, so this is the for all quantifier. There's one other quantifier, the there exists quantifier. We write it as a backwards e, and it's like our previous quantifier, but now it's like an or. Okay, so just to give you an example of the difference between these two, let's keep our same sets x and our element y as before, and now we could say that there exists little x in the set x such that y is strictly larger than x. So what does this mean? It means that either y is greater than x1 or y is greater than x2 or y is greater than xn. So it means that we know that y is bigger than at least one element of the set, but not all of them, as in the previous case. Well, it could be all. All we know is that y is bigger than at least one. Okay. So now we're going to do something a little bit more complicated. We're going to talk about how do you compose logical quantifiers together. Composition of logical quantifiers. We are on page 5. Okay. So this is just a sequence of qualified claims. Okay, so let's just do an example. It's the most clear way to understand this. So what if we said, for every x in x, and for every y in y, x plus y less than or equal to 1. So here just assume that x and y are subsets of the real numbers. Okay, so here's one statement. So you read this for all x and x, for all y and y, x plus y is at most 1. So here's an alternative statement that I want you guys to tell me, is this the same or is it different? For all y and y, for all x and x, x plus y less than or equal to 1. So it turns out that these two are the same. They're actually saying the same thing. Well, let's look at another example where we use a different kind of qualifier, and this won't be the case. So we can instead say, let's look at a slightly different claim. For all x and x, there exists y in y such that x plus y is equal to 1. So this is, I changed this to equality just because it would make more sense. So what is this saying? We have the set x, we can pick any guy, and we can find a second guy in the set y such that their sum is 1. Now let's say that we change it. For all, there exists y in big Y such that for all x in big X, x plus y is equal to 1. Okay, so I'm going to claim that these two statements are different. So we can't always just switch the order of our qualifiers or quantifiers. So why is that the case? Let's just look at a very simple example. Let's say that x is a half third and y is x is 1/2 2/3, y is 1/2 1/3. Okay, so let's just see for these two sets if the first statement is true and if the second statement is true. So looking at the first statement, for every x and x, so let's just pick 1/2 first. There exists y such that x plus y is 1. So if we pick x to be 1/2, we could find y to be 1/2 such that their sum is 1. And if instead we picked x to be 2/3, we then pick y. We pick 1/3 from y such that their sum is 1. So this statement is true. Okay, let's look at the second statement. There exists y such that for all x and x, x plus y is 1. So we're going to have some trouble here because if we pick y to be 1/2, then it has to be the case that 1/2 plus 1/2 is 1, and 1/2 plus 2/3 is 1, and both of these can't add up to 1. So we'll have the same problem if we try and pick y as 1/3, right? So you can't. What I'm getting here is that the order of the quantifiers is very important, and when you try and state theorems, you're going to state it very precisely using these quantifiers. So you want to learn how they work. So in general, we have a rule. You can only exchange the order of quantifiers of the same type. Right, so up here we could exchange two for alls and it didn't change the meaning of the statement. And the same with if you have two consecutive there exist quantifiers, you can exchange their order. Okay, so next let's talk a little bit about the negation of qualifiers. And here we're going to use something called the Morgan's rule. Okay, So if you remember De Morgan's rule, you've seen it in logic before, just kind of basic logic. So if we had not, so let's just say that A is a statement that is true or false. A and B, we know that this is equivalent to not A or not B. So here A and B are both statements that are either true or false. And then whether or not this entire statement is true is equivalent to whether or not this entire statement is true. This is De Morgan's rule. It's very easy to convince yourself of this. And the second rule is very similar. Not A or B is not A and not B. So what we see going on here is that we can move the not inside this conjunction here, but we have to flip the A to be, so we can change the A and the B both to be nots, but then we have to change the and to an or. And likewise, if we do this here, we have to change the or to an and. Okay, so remember that before I was saying that for all is basically an and there exists is or. So we get the following rules. Well, let's just do an example. What if I want to say it is not the case that for all x and x, x is strictly larger than y. Okay, so if I just kind of do the De Morgan thing here, I know that when I move the not inside of the quantifier, I have to flip the type of the quantifier from an and to an or. So this is saying there exists x in x. And now I can take the not such that not x greater than y, but this is silly. We don't want to say that. We want to say x is less than or equal to y. So are these statements equivalent? Let's look at it. We originally want to say that it is not the case that for every x, x is larger than y. But what does this mean? It means that there is some x out there that is no more than y, and that is the second statement. So hopefully now you kind of see how to do this. You just basically apply De Morgan's rule. You move the not inside qualifier, and then you negate the internal statement after flipping the qualifier. So let's just do a more complicated example. So let's say that we want to say it is not the case that for every epsilon greater than 0, there exists n in C plus, yes, such that for all n greater than n, xn minus x is less than epsilon. Okay, so here we have xn is some sequence in R, and x is in R. Okay, so if you haven't taken analysis, this probably looks a little bit intimidating. But if you are familiar with the topic, you should hopefully recognize that what I'm saying here is that the sequence xn converges to x. That this is just a way of writing down a limit in terms of these formal expressions, in terms of these quantifiers. Okay, so let's try and negate this and see what we get. What does it mean if sequence xn does not converge to x? So what do? We need to flip this quantifier. So there exists epsilon greater than 0. We need to flip the quantifier such that for all n in z plus, again, then we have a for all, so we're going to have to flip the quantifier. There exists little n bigger than big N, such that now we get to negate the last statement. xn minus x is at least epsilon. So what this is saying is that no matter how small we take epsilon, if we can go far enough out, no, I said that wrong. What this is actually saying is that there is some epsilon, potentially very small, such that no matter how far we go out in our sequence of xn, if we look even further, we'll find some guy where we exceed our error tolerance of epsilon. That's what it means for the limit not to exist. Okay, so this is something that you want to kind of familiarize yourself with, this technique of negating quantified statements, because it's very helpful when you're writing proofs. So hopefully you guys will practice that a little bit. Okay, so I guess in the interest of time, I'm going to skip this little section on set operations. This is just talking about infinite unions of sets and infinite intersections of sets. But David's going to talk about that in class, so I guess I'll skip it for now since we're running out of time. And there's also a De Morgan's rule for sets. That's in the notes, but I'm not going to do that right now. Next, I want to talk about Cartesian products. So this is a very important topic. So we are on 7. Okay, so what is a Cartesian product of two sets? So we have sets A and B, and the product is, we're going to write it as A times B. What is it equal to? Here are all the points x, y, such that for all x in A, for all y in B. Okay, so basically for every possible pair from A and B, we make a new element. Okay, so let's just do a really simple example. Let's say A is red and blue, and B is -1, 0, and 1. Then A cross B is just going to be, it's going to have 6 elements. I'm just going to write R for red, red, -1, red, 0, red, 1, blue, -1, blue, 0, blue, 1. Okay. So let's do something a little bit more complicated. So let's say that x is the half line 0, infinity, and y is the other half line -infinity to 0. What is their Cartesian product? Well, you can kind of just draw it on the xy plane. X times y is the following set of points. So if here's our x-axis, here's our y-axis, it's going to be down here. X times y. So y, because the x things have to go from 0 to infinity, and the y's go from 0 to negative infinity. So that's x cross y. Okay, so a little bit of shorthand. If we take a set cross itself, so x cross x, we would just write this as x squared. And so before, when we had r squared, this is just r cross r. It's a, so hopefully you guys see that. You've probably seen R2, you've seen R3. If you took multivariable calculus, this is very important in physics. But we're going to be looking at actually much higher dimension spaces. Okay, so we actually can extend this idea much further. So let's say that we have a collection of sets, and we want to take the product of all of them. Product of a collection of sets. Okay, so we have our sets are going to be denoted A1, A2, A3, and it's just going on. Maybe it's finite, maybe it's an infinite list. So then we can write product from I equals 1 to n of AI. What do we mean by this? We just mean A1 cross A2 cross A3. Or alternatively, we could, if we had an infinite, we want to take an infinite number, we could say I equals 1 to infinity of AI. And now it would just never stop. Okay, so what do we mean by this? This may look a little bit confusing, so let's just give a very simple example. So what if I want to say that let's let n be the numbers from 1 to n, and I want to know about the set of all subsets of n. So an example of a subset of n would be like 1, 3, 4, or 1 through n. The complete set n is also a subset of n. Okay. Also, the empty set is a subset of n. So how would I write this down in terms of Cartesian products? Okay, so let's let AI have two values. Include I or exclude I for I equal 1 up to n. Okay. So what do we do from here? So let's look at the Cartesian product from I equals 1 to n of AI. So what will an element of this tell us? It will say include 1, exclude 2, include 3, include 4. So essentially, from this, we can exactly, each element here tells us something like 1, 3, 4 subset of n. The elements of this all correspond directly to these subsets of n. Okay, so what we've seen here is that this gives us a system to enumerate the subsets of n. And so the shorthand for this is we're going to say 2 to the n is this set. Okay, so maybe you're asking, so where did this 2 come from? What is this notation? So I'm going to come back to that shortly. We're going to have to take a little bit of an interlude first to get there. So something we haven't actually talked about yet is the cardinality of a set. Okay, so what is it? It is just definition. Cardinality of A is the number of members. My pen is dying. I have a new pen. Number of members of A. And sometimes we're going to write it down like this, cardinality of A. That's how we'll write it down. Okay, so let's just do a stupid example. If A is just 1, 2, 3, 4, then the cardinality of A is 4. Okay, so let's let B be 1, 2, 3. So here's a question. What is the cardinality of A cross B, right? And so kind of, if you're just going to play it out, you see that for each element of A, we need 3 elements from B. For each element of A, because there's 3 elements in B, we get 3 different possibilities. And there's 4 elements in A, so this should just be 4 cardinality of A times cardinality of B, 4 times 3. Right? And this rule actually applies in general. So if you have the Cartesian product of 2 different sets, then, or if you have the Cartesian product of any number of sets, A times B C, or whatever. We'll just leave it at that. It's just cardinality of A times cardinality of B times cardinality of C. And so now you see why did we call A times A? We said this was just A squared, and it kind of makes sense because now cardinality of A times A is cardinality A times cardinality A, or cardinality of A squared. So that's nice. Okay, so now getting back to the previous page, we were talking about the set 2 to the A. What is a cardinality of 2 to the A? Well, because remember that for this was just the set of all subsets of A. So we have essentially a bunch of this is the same thing as A1 times A2 times a cardinality of A, where here A1 is just a set, include the first element of A or exclude the first element of A, right? So that's this. So if we take cardinality, we can just apply our rule now, and we get 2 times 2 times 2, and there are going to be cardinality of A terms. That's why we just get 2 to the cardinality of A. So this is why we call the set 2 to the A, because its cardinality is 2 to the cardinality of A. Okay, so now from here, I guess we have an interesting question. What is the cardinality of the set Z? And also, what is the cardinality of the set R? These are kind of difficult questions because these sets have infinitely many members. But we have the feeling there's a whole lot more real numbers than there are integers. So this is going to be what I'm trying to spend the rest of our time convincing you of, is that these sets should have a different cardinality. We're going to talk about how to define that. But in order to do that, we're going to have to take another short detour. Actually kind of a long detour. So I want to define formally, in terms of the analysis definitions, what is a function. So we are on page. So you guys have seen functions. You're presumably all of college, before college. But for the purposes of this class, let's just say it is a map. It maps elements of a domain X into the codomain Y. So here, X and Y are just two different sets. So this is what a function is going to do, but this allows for freedom. We need to restrict it a little bit. So definition: a function is a subset of X cross Y, the Cartesian product, such that for every X in the domain, there is exactly one point of the form X dot, so just some other guy in our function. So it's a subset of X cross Y, where we have exactly 1 point of little x for every little x in the domain. So we'll give examples in a second if you find this formal definition a little bit unclear. But just first a little notation. So we write this as f is a function that maps x to y. And we say f maps x to y. Okay. And just as a side note, there's a little colon here. If you're using LaTeX, don't write Don't write the following. Don't write f colon x to y, right? F colon / colon x to y. If you do it this way, the spacing is wrong. You should do it this way. Okay, so returning to reality. Let's give an example. Okay, so let's just give a really simple example. It's not even in my notes and included for some reason. Let's just say that f of x equals x squared. So for this function, what is the domain? What is the codomain? So we could take the domain to be all of R, right? This is defined for, does it meet our definition? Well, let's take the domain to be all of R. Let's take the codomain to also be all of R. Does it meet our definition? So for every point in our domain, our function uniquely determines some point in the codomain. So if we pick x to be 0, it will result in the point 0 in the codomain. If you pick x to be 1, it will result in 1 from the codomain. If you pick x to be -1, it will result to be 1 in the codomain. But it's never the case that there's 2 possible assignments in the codomain for 1 point in the domain. So this is a function. Now you may notice that we aren't using the entire codomain. We could instead take the codomain to be R plus, the non-negative real numbers, because we don't really, our function will never land on a negative number. But it's fine. You can define it either way, and it still works. We don't have to use the entire codomain. Okay. So here's a much more difficult question. Let's say that x and y are finite sets. How many unique functions are there from x to y? Okay, so what do I mean by unique? I mean that, well, we'll say 2 functions are equal if for every input in x you get the same output in y. So maybe let's just try and count these out. So for each element of x, we get to make y different decisions, right? So essentially, for the first element, we make y, so we get y decisions for the first guy, and we get y decisions for the second guy, and you multiply these together to count, and we're going to do this x times. Cardinality of the set x times, so the total number of functions is going to be y raised to the x power. And as a result, kind of just a shorthand notation, you don't really have to know this for the purpose of this class, is y raised to the x is the set of functions from x to y. Okay, if you didn't get that, don't worry about it. It's not really super relevant for the course. It's kind of fun. Okay, so I guess we are running out of time, but I really do want to talk about how to count the integers and how to count the real numbers. So I'll try and go quickly. Now on page 11. So on the notes online, you'll see a little bit about like the pre-image here. Don't worry about that for now. It will be important later in the course, but we're not going to talk about the image and the pre-image. Okay, so we'll just do a few definitions really fast. Definition. A function is one-to-one if f of x equals y implies that for all x prime and x prime not equal to x, f of x prime is not equal to y. Okay, so what is an example of a function that is one-to-one? What is an example of a function that is not one-to-one? Okay, so let's compare the functions f of x is equal to x cubed and g of x is equal to x squared. Let's just plot these guys. So here, this is what x cubed looks like approximately. So here's f of x. Over here, this is g of x, and this is x. Okay, so I'm going to claim here that f is one-to-one, but g is not. So why is this the case? So why is g not one-to-one? Well, let's just, for example, look at 1 and -1. Here, both functions take the value. The function g of x takes the value 1 when x is 1, and takes the value 1 when x is -1, right? So that's kind of violating this condition here, which says that if f of 1 is equal to 1, then f of -1 should not be equal to 1. So this is not one-to-one. But here we see that f of x, this is a one-to-one function, and that the value of f of x is uniquely determined by x. Okay, so definition number 2, a function is onto if for all y in the codomain there exists x in the domain such that f of x is equal to y, right? So again, the function x cubed is onto because we hit every value in the domain. We'll hit every y from -infinity to +infinity. Whereas g of x, if we take the domain and codomain to be all of R, then we're not going to hit everything because we're never going to produce negative values. But if, for example, we restricted the domain to be if we restricted the codomain to be 0 to infinity, then the function would be onto as well. So what's important here is that whether or not you restrict the definition of the codomain is very important in defining whether the function is onto. Okay, so finally, a function is a bijection if it is onto and one-to-one. Okay, so bijections are going to be important here because we need them to define, well, we'll see why they're important. But again, the function x cubed, it was one-to-one and onto, so it's a bijection, whereas the function x squared was not, at least on, yeah. So the function x squared was definitely not one-to-one under any definition. However, if we restricted the domain to be here, and we restricted the codomain to be here, then our function x squared is both one-to-one and onto. So it's a bijection on this restricted domain and codomain. Okay, so I think we're on page 12. Okay, so let's return to cardinality. So definition. A function. A set x is countably infinite if there exists a bijection between x and z, where z is the integers. So let's just give some examples. Example. I claim that the set z plus is countably infinite. This may be a little bit surprising. Z plus is half the size of z, but I'm saying that it's countably infinite, which means that they have the same cardinality. So countably infinite is a cardinality. So why is this the case? So here's how you can set up the bijection. The simplest way to do this is just to arrange a table. So here are the elements of z plus. 1, 0, 1, 2, 3, 4. Okay, and here are the elements of z, and here's a simple algorithm that will do it for us. Our function, it's going to go from z plus to z and back, so it's a bijection. Take 0 to 0, 1 to 1, 2 to negative 1, 3 to 2, 4 to negative 2, 5 to 3, 6 to negative 3, and so on. So you can write down a formula. I worked out a formula for this. I hope it's the same as in this table. I said that f of x is x over 2, or x even, and negative x plus 1 over 2, or x odd. Okay. And you can see here that this function is it's easy to see this function is 1 to 1 and onto, right? Because we know that we're never going to repeat some value from z here, because our numbers are just always increasing in absolute value. So we know that it is 1 to 1, and we know that it's onto because eventually we're going to hit every single integer by using this procedure. So this is kind of the easy way to verify that something is a bijection. So I just want to add in something here quickly in the definition. A set is countable if it is either countably infinite or finite. Okay, so let's go through some of the rules that we can derive for when sets are going to be countable. I think we're on page 13 now. Okay, so theorem. If x and y are both countably infinite, then x union y is countably infinite. Okay, so how do we do this? Well, we can do the table proof again. Proof. I'm just going to draw the table, so it's really easy. So we need to make a bijection between z plus and x union y. Okay, so technically, the way I defined whether or not something is countable, we should make a bijection between z, but we know that because if you compose two bijections, you have a bijection. You can just make a table against z plus as well, and that doesn't matter. So 0, 1, 2, 3. So what's our strategy here? We can just we can enumerate, since x and y are countable, we can enumerate their elements. So we can say x is x1, x2, x3, ... and same for y. We can say that y is y1, y2, ... So here is going to be my strategy for enumerating x union y. you say x1, y1, x2, y2. Okay, so clearly we're going to get every element of x and every element of y if we use this procedure. Okay, but what's a problem with this procedure? The problem is that what if x and y share an element? Then our function is going to repeat some elements, so it's not going to be a bijection. But you can kind of easily amend this by just, instead of doing x and x union y, we can instead say x. We replace y by y tilde, where this is y set minus x. And then we replace x union y by x union y tilde because they're the same thing. And now these two sets will have no common elements. Okay, so that was pretty easy, but let's try something a little bit harder. So theorem, if for all I in some set that is countable, AI, there's some set AI is countable. I is countable. Okay. Then, well, you could say countable or countably infinite. The theorem is true in either case. Union from I in the index at I of AI is also countable or countably infinite. And the proof, so all we need to do is find an enumeration strategy that will hit everyone, but not hit anyone twice. So let's let A super I sub n be the nth element of A I tilde, where this tilde business is just, again, to get rid of the, to make the sets disjoint. So where A I tilde is just, it's just AI without all the previous sets from j equals 1 to I minus 1 of aj. So we're getting rid of all the people who came before, and that's ai tilde, and a super I sub n is the nth element of this set. And we know we can enumerate them because these sets are countable. So here's our enumeration order. I'm not going to draw a table like before. I'm going to draw a two-dimensional table, actually. So we're going to start with A1, 1. The next will be A2, 1, A1, 2, A3, 1, A2, 2, A1, 3, and so on. And we're going to proceed in this order. So what is this doing? We start out in the first row. We only pick the first guy of the first set. In the second row, we pick the first guy of the second set and the second guy of the first set. In the third row, we pick the first guy of the third set, the second guy of the second set, the third guy of the first set, and so on. And you can see that eventually we're going to get every guy from every set. So this, because we can enumerate everything, this means that the set is countable. Okay, so we have two examples left. I'm out of paper. Maybe I have some more here. Okay. Lucky, or maybe unlucky for you guys, I do have a little more paper. This remains on camera. Okay, so here's a question. Are irrationals countable? Okay, so as a reminder, what is a rational? A rational number is of the form P over Q, where P and q are integers. And q is not equal to 0. So I mean, you could add some rules saying that p divided by q must be unique, so you don't want to include the same rational numbers more than once. But it's not really relevant for this conversation here. So what I'm going to claim here is that the Cartesian product theorem, Cartesian product of countable sets is countable. Okay, and why would this imply that the rationals are countable? Well, the rationals are a subset of the Cartesian product of z. Let's just see. Okay, so here's the proof. We need to define an enumeration order for the Cartesian product of z plus and z plus. So let's just put p over here and q over here. And let's just draw out all the integer points in this lattice. So I'm drawing a lot of integer points, but we don't need this many. Okay, so we can start here. So I want to take z plus cross z plus and find a way to enumerate all these points. So I can go from here to here to here, up to here, kind of wind back down here. So you see there's a pattern into what I'm doing. And so if we're to proceed in this manner, and let's say we need to map, we need a bijection between z plus and z plus cross z plus 0, 1, 2, 3. Okay, so here 0, 0 was the first guy we explored. At 1, we explored 1, 0. At 2, we explored 0, 1. At 3, we explored 0, 2, and so on. Right? So this gives us a rule for how to get back and forth between z plus cross z plus and z. So I mean, even though the Cartesian product has way many more points than z, they're still of the same cardinality. And the rationals here are just the quotient of p and q, but we're going to actually take even fewer points. And it also is the case that a subset of a countable set is still countable, and you can prove that using the rules we've already introduced. I don't want to dwell, though. The most important thing here is that the Cartesian product of countable sets is countable and that the rationals are countable. Okay, so what about the reals? So these guys denote as R. But for simplicity, what about the set 0, 1? All the real numbers between 0 and 1. Is this countable? Everything we've seen so far has been countable. So you may think it's countable, but it turns out it's not. So the first question we have to ask is, what is a real number? The definition of a real number is actually pretty complicated. But a simple definition that will do for our purposes, which is it's actually not exactly right. But let's just say that a number in 0, 1 is an infinite binary expansion. Binary decimal expansion. For example, 0.001101101101. It goes on forever. That is one example. This is one way that you can define real numbers. There's a few problems with the definition, actually, because you could have multiple representations for two different numbers. For example, if you have something that ends in repeating ones, it's like ending in repeating nines if you were to be in base 10. And you know that if something ends in repeating nines, it's the same thing as just kind of rounding it up. But putting these technicalities aside, what if we just wanted to count the number of real numbers, assuming that each real number corresponded to one of these decimal expansions? So what is this? Let's say that let's let di be either 0 or 1, and this corresponds to the ith digit of our number. Right? Then our real number, the set of all real numbers in the interval 0, 1, is the same thing as the Cartesian product from I equals 1 to infinity of di. Right? So each di is of size 2. So we could just kind of apply our rules from before. It'd just be 2 to the infinity, which is infinity. So that's not super helpful. So we need to do something better to determine if the set is countable or not. Can we put it in bijection with the integers? So I claim that we cannot. Theorem. The set is uncountable. Okay, so the proof is actually surprisingly simple, but maybe not so intuitive. So assume for contradiction it work. What does this mean? It means that we can enumerate the elements of the set. So let's let R superscript I be the ith real in 0, 1 for our countable enumeration. Okay. And we're also going to let R super I sub j be the jth digit of R super I. Okay, so now we're going to let R star, this is, we're defining some other real number, have R star, the jth digit of R star, be 1 minus the jth digit of R j. Okay, so what does this mean? Let's just do a little simple table over here. So if here's R1, here's R2, here's R3, and here's the first digit, here's the second digit, here's the third digit. So let's say it was 1, 1, 1, 1, 0, 1, 0, 1, 1. What's important is what's along the diagonal, because we have this RJJ term. So we would have R1 star be 1 minus this, or 0. We would have R2 star be 1 minus 0, which is 1, and R3 star be 1 minus 1, which is 0, and so on. Okay? So what is funny about this number? What's funny is that for all I, R star is not equal to Ri because they differ on digit I, right? So why is this a problem? It's a problem because the set of points Ri we're supposed to enumerate are the set that we're trying to prove is countable. We assumed it was countable for contradiction, which means that the Ri should enumerate everything in the set, but we've just proven we found an element that is different from every single guy in the set, which means that he's not actually in the set. So therefore, R star is not in this Cartesian product, but R star is going to be a number in 0, 1, and this creates a contradiction. So this completes the proof. So I guess now, if you've not seen that before, you've now seen it. You've seen that there are an uncountable number of real numbers. Okay, so I know that kind of wraps up what I wanted to cover today. I know we covered a lot of material. It was pretty fast. And in the future, we're going to go slower and we're going to talk about probability, not about real analysis. But these are the kind of basic tools that you need to do well in this course. So hopefully you have absorbed this. All right, thanks.